Draw a map of your city but locked you in one crowded neighborhood and never let you leave. You would see streets and buildings around you, but you would have no idea what the whole city really looks like. That is exactly the problem astronomers face with the Milky Way. We live inside it. We are stuck on one little spiral arm, trying to understand an entire galaxy that wraps around us on all sides. No wonder we misunderstood it for so long. For centuries, even very smart people were basically guessing. When you look up at the night sky, it feels like you see everything, but you really do not. Astronomers still do not even know the exact number of stars in the Milky Way. Current estimates range from about 100 billion to 400 billion stars, which is a huge margin. That is like trying to guess the population of a country and only being able to say it is somewhere between India and a small continent. The fact that we cannot narrow it down more tells you how hard this problem really is. Even something as basic as the shape of our galaxy is not fully settled. You would think by now we would know exactly how many spiral arms the Milky Way has, but scientists are still debating whether there are 2 major arms or 4 main arms. The reason is simple and frustrating. Observing other galaxies is surprisingly easier. With those distant spirals, we get a nice clean top-down or side-on view. With the Milky Way, we are trapped in the disk looking through it edge-on from the inside, and the view from the inside is messy. Between us and the center of the galaxy, there are enormous clouds of gas and dust. These clouds are beautiful in long-exposure photographs, but they are also cosmic smog. They block visible light and hide vast regions of the galaxy from our eyes and from ordinary telescopes that see only in visible wavelengths. The region toward the galactic center is so crowded and dusty that astronomers literally call parts of it the zone of avoidance, because traditional surveys simply could not see through it. Visible light is easily scattered and absorbed by dust, so when we tried to map the Milky Way using only optical telescopes, it was like trying to explore a mansion with a weak flashlight in a smoky room. Large sections of the structure simply vanished behind the haze. That is why infrared light and X-ray observations became absolutely crucial. Infrared light has longer wavelengths that slip through dust more easily, revealing stars that were completely hidden before. High-energy X-rays can escape from extreme environments near the center, carrying information from regions we cannot see in visible light at all. So for a long time, astronomers had to piece together a model of our galaxy from incomplete clues, like detectives reconstructing a crime scene with half the evidence missing. Star counts in different directions, radio maps of hydrogen gas, motions of star clusters, all of it had to be combined just to sketch a rough outline. It is not that scientists were careless. They were trying to map their own house while locked in one room, with most of the doors sealed and the lights turned low. Our misunderstanding of the Milky Way lasted for centuries because our tools were simply not powerful enough. That is exactly why a new generation of missions, especially one spacecraft in particular, would change everything and finally start to give us a true 3-dimensional picture of our home. That new generation spacecraft finally arrived, and it changed everything. The mission was called Gaia, and what it accomplished was nothing short of revolutionary. Over the course of more than 10 years in space, Gaia mapped over 2 billion stars, making more than 3 trillion individual observations. Think about that for a moment. 3 trillion observations. That is not just a big number, it is an entirely new way of seeing our galaxy. But how exactly did Gaia do this? The answer comes down to an old trick used in a completely new way. The technique is called parallax, and you have actually experienced it yourself. Hold your finger out in front of your face and close one eye. Now switch eyes. Notice how your finger seems to jump against the background? That is parallax. Your 2 eyes give you 2 slightly different perspectives, and your brain uses that difference to figure out how far away your finger is. Gaia used the exact same principle, but on a cosmic scale. As Earth moves around the Sun over the course of a year, Gaia observed stars from different positions in that orbit. A nearby star will appear to shift slightly against the distant background stars, while a faraway star will barely move at all. The larger the apparent movement, the closer the star. By measuring these tiny shifts with incredible precision, Gaia could calculate distances to stars across the galaxy. And when we say incredible precision, we mean it. Gaia could measure angles down to micro-arcseconds, which is like being able to see a coin on the moon from Earth. No telescope before Gaia had this level of accuracy. The spacecraft used Earth's entire orbit as its measuring baseline, a distance of about 300 million kilometers, and it watched stars shift back and forth as our planet circled the Sun year after year. But Gaia did not just measure distances. It also tracked how fast stars are moving, how bright they are, what they are made of, and even their masses. Every star that Gaia observed was scanned repeatedly, building up a detailed profile over time. The result was the most detailed three-dimensional map of the Milky Way ever created. For the first time in human history, we could see our galaxy not as a flat smear of light across the sky, but as a vast dynamic structure with depth, motion, and history. Before Gaia, we had measured accurate distances to only a few thousand stars. Gaia increased that number by a factor of 10,000. It gave us parallax measurements for over 1 billion stars, revealing the architecture of spiral arms, the thickness of the galactic disk, and the shape of the central bulge. Suddenly, the Milky Way was not a mystery anymore. It was a place we could actually map and explore, at least with data. And that data revealed something absolutely shocking. Hidden in the motions of those 2 billion stars, Gaia found evidence of something we never expected. Something that happened billions of years ago. Something violent. When astronomers started analyzing Gaia's data, they noticed something bizarre. Among the billions of stars orbiting peacefully around the galactic center, there were about 30,000 stars moving in completely the wrong direction. These were not just going a little slower or a little faster. They were moving on strange, highly elongated orbits that plunged them deep into the heart of the Milky Way and then flung them back out again. It was like finding cars driving backward on a highway. Something had thrown them off course, and that something had to be violent. The evidence did not stop with their weird motion. When scientists analyzed the chemical makeup of these stars, they found another clue. These rebellious stars had different compositions compared to normal Milky Way stars. They were outsiders. They did not form here. They came from somewhere else. The only explanation that made sense was that these stars were the remnants of another galaxy, a smaller galaxy that had collided with the Milky Way billions of years ago. Scientists named this devoured galaxy Gaia Enceladus. It smashed into our galaxy somewhere between 8 and 11 billion years ago, back when the Milky Way was still young and growing. The collision was not a gentle merger. It was a head-on crash. Gaia Enceladus was ripped to shreds by the immense gravitational forces of the much larger Milky Way. Its stars were scattered across our galaxy's halo, and their strange orbits are the frozen memory of that ancient violence. But the impact did more than just add stars. The collision may have fundamentally reshaped the structure of the Milky Way itself. Some astronomers believe that the crash puffed up, or even fractured the Milky Way's disk, forcing the galaxy to regrow a new disk afterward. The debris from Gaia Enceladus helped form the central bulge at the galaxy's heart and contributed to the stellar halo that surrounds the main disk. In other words, this ancient collision is part of the reason the Milky Way looks the way it does today. And here is the truly wild part. Gaia Enceladus was not the only victim. The Milky Way has eaten multiple galaxies. Another dwarf galaxy, called the Sagittarius Dwarf Spheroidal, is being absorbed right now. Astronomers can see streams of stars being pulled off it, as the Milky Way's gravity tears it apart. Within the next billion years, Sagittarius will be completely gone, digested into the growing mass of our galaxy. In fact, astronomers now believe the Milky Way may have cannibalized as many as 6 different galaxies over its lifetime. Some of these mergers happened recently, at least in cosmic terms. Evidence suggests that one significant merger might have occurred just a few billion years ago, far more recently than scientists originally thought. Each of these collisions left wrinkles in the distribution of stars, like ripples frozen in time. Gaia's precision allowed us to see those wrinkles and trace them back to their violent origins. So the Milky Way is not just a static spiral sitting peacefully in space. It is a cannibal, a growing monster that devours smaller galaxies and adds their stars to its own. And every one of those stolen stars is still out there, moving in strange patterns, waiting to tell its story. If the Milky Way has spent billions of years colliding with and eating other galaxies, that already makes it feel much more alive than a simple textbook picture. But there is another surprise hiding in plain sight. Look at almost any picture of a spiral galaxy, and it seems obvious what is going on. You see bright spiral arms, so it is natural to imagine those arms as fixed structures, like the rigid blades of a fan, with all the stars stuck in place and rotating together. That picture feels so intuitive that for a long time it shaped how people thought about spiral galaxies. The problem is that this simple idea completely fails. If spiral arms were permanent solid features, then as the galaxy rotated, the inner parts would complete their orbits faster than the outer parts. Over time, the arms would twist tighter and tighter, winding up like a piece of string being twisted from one end. But when astronomers compared this idea to what is actually observed, the math did not work. Real galaxies have been around for billions of years, yet their spiral arms are not hopelessly wound up. So, something about that mental image had to be wrong. The key insight is that galaxies do not rotate like solid disks. Instead, stars at different distances from the center move at different speeds. The bright arms are not rigid objects, they are patterns, regions where stars and gas are temporarily crowded together. The best way to think about them is as density waves. Imagine cars on a busy highway. Traffic jams appear as slow-moving clumps that cars enter and leave. The jam itself moves along the road, even though no individual car is permanently stuck in one exact spot. Spiral arms behave in a similar way. Stars move in and out of the arms as they orbit the center of the galaxy. A star may spend some time inside a spiral arm where conditions are denser, and then eventually drift out into a less crowded region. The arms look bright, not because they hold special stars forever, but because something important happens inside them. The extra density compresses clouds of gas, and that compression triggers star formation on a massive scale. Newborn stars are very hot and very bright, especially the massive blue stars that burn intensely and die young. These young blue stars light up the arms, tracing the wave pattern that sweeps around the galaxy. By the time those massive stars explode as supernovae, they have not traveled far from where they were born, so the arms remain defined by their glow. What you see in the photographs is not a permanent structure frozen in place, but a moving wave of star birth unfolding across the disk. This idea of density waves does not just apply to galaxies. Similar patterns appear in Saturn rings, where regions of higher particle density form striking bands and gaps. The rings are full of ice and rock particles orbiting Saturn, but gravitational interactions create wave-like features that move through the system. In both cases, the pattern can be long-lived, even though the individual pieces never stay put for long. Understanding spiral arms as density waves solves the winding problem, and explains why the arms of galaxies can persist for billions of years without twisting into chaos. It also changes how we think about our own place in the Milky Way. The Sun is not anchored to a fixed arm. It is moving through these waves, experiencing changing environments over cosmic time. And once you accept that the stars are not simply orbiting in neat circles, you are ready to confront an even deeper puzzle about how fast they move and what that says about the hidden mass that holds galaxies together. We saw that stars do not just glide around the galaxy in neat little circles. They move through waves, through spiral arms, through the debris of ancient collisions. That already feels wild. But when astronomers measured how fast those stars are actually moving, they found something even stranger. The motions do not match what visible matter alone can explain. It is as if there is an invisible hand gripping the galaxy and refusing to let it fly apart. Here is the basic puzzle. Take all the stars, gas, and dust that we can see in a galaxy and add up their mass. Then use Newtonian gravity to predict how fast stars should orbit at different distances from the center. If only visible matter were present, stars far out in the disk should move more slowly, just like planets in the outer solar system orbit more slowly than those close to the Sun. But when astronomers measured actual star speeds, they saw something completely different. The outer stars were moving too fast, almost as fast as stars much closer in. Those measurements gave what are called rotation curves. Instead of dropping off with distance, the curves stayed almost flat. That meant the outer parts of the galaxy had more gravitational pull than all the visible stars and gas could provide. If there were no extra mass, many of those fast-moving outer stars would simply escape into space over billions of years. Yet they do not. They stay bound. So there had to be something else. Something invisible adding extra gravity. Astronomers call this missing mass dark matter. It is not dark in the sense of being dirty or evil. It is dark because it does not emit light, reflect light, or absorb light in any way that our telescopes can directly detect. It does not glow, it does not block other light, and it does not behave like ordinary protons, neutrons, and electrons. We only know it is there because of its gravitational effects. It pulls on stars, on gas, on whole galaxies and galaxy clusters, shaping their motions over cosmic time. The current picture is that every large galaxy, including the Milky Way, sits inside an enormous halo of dark matter. This halo extends far beyond the visible disk, like an invisible scaffold. The stars and gas are just the bright frosting on the surface of a much larger, unseen structure. When you feel puzzled by those flat rotation curves, dark matter is the simplest way to make the equations work. Add a huge halo of invisible mass, and suddenly the star speeds make sense again. Dark matter did not just affect the present-day motions, it also played a crucial role in how galaxies formed in the first place. In the early universe, tiny clumps of dark matter began to collapse under their own gravity, creating wells that attracted ordinary gas. That gas cooled, condensed, and eventually formed stars and galaxies. Without those dark matter seeds, the expansion of the universe would have stretched matter apart too quickly for galaxies to form as we see them today. Observations of very distant early galaxies suggest that their rotation patterns and structures were different, reflecting the way dark matter and normal matter were still settling into balance. Over billions of years, as more gas fell in and more stars formed, dark matter continued to guide the growth of galaxies, influencing their shapes, their sizes, and their internal motions. In a very real sense, dark matter is the hidden architect of galactic evolution. So when you look at a spiral galaxy, you are really seeing two things at once. There is the luminous part that our eyes and cameras can capture, with its bright arms and glowing star-forming regions. And wrapped around it, there is a massive, invisible halo that holds everything together and quietly controls the dance. But dark matter is not the only extreme phenomenon that shapes galaxies. At their centers, something even more dramatic waits, devouring matter, and launching jets that can outshine entire galaxies. By now, Gaia has already helped reveal the dark matter skeleton of our galaxy and the scars of ancient collisions. But one of the most astonishing things about this mission is that it did not stop at mapping stars in the Milky Way. Once you can measure positions and motions with extreme precision, the entire sky turns into a laboratory. Gaia started as a galactic cartographer and ended up becoming a kind of all-purpose explorer for almost everything that moves or shines. Close to home, Gaia tracked hundreds of thousands of objects inside our own solar system. It has detected well over 150,000 asteroids and measured their orbits with exquisite accuracy. Some of these are in the main asteroid belt, some are near-Earth objects, some belong to more exotic families. By watching tiny shifts in their positions over time, Gaia even discovered hundreds of binary asteroid systems, where two asteroids orbit a common center of mass like a miniature double star. That kind of detail helps scientists understand how these bodies formed, how often they collide, and how their orbits might change in the future. Because it observes the sky repeatedly over many years, Gaia can also roll time forward and backward. Once you know how stars are moving now, you can predict where they will be in the future, or where they were in the past. Using that information, astronomers can map stellar motions millions of years ahead, tracing streams of stars as they drift around the galaxy. Some of those motions revealed something even more dramatic. Gaia helped identify a black hole candidate roughly 33 times the mass of the Sun, lurking relatively nearby in our galactic neighborhood. It does not emit light itself, but its gravitational pull on a companion star gives it away. Gaia does not just focus on our galaxy. Its sensitivity allows it to pick up incredibly distant objects called quasars. These are powered by supermassive black holes in the centers of faraway galaxies, and they are so luminous that they can outshine all the stars in their host galaxies combined. Gaia has catalogued over 1 million quasars, turning them into fixed reference points to anchor its map of the sky. At the same time, its ability to read stellar spectra and colors means it can identify stars that formed in the very early universe, older than many galaxies we see around us today. With that combination of ages and motions, Gaia can trace how stars have migrated over billions of years. Some stars that are now near the Sun were born far away in different parts of the disk. Others were pulled in from ancient mergers and now move on tilted orbits through the Milky Way. When astronomers plot these motions in 3 dimensions, they see that the disk of the Milky Way itself is not a perfectly flat calm sheet. It is slightly warped and wobbling, like a spinning record that has been bent and nudged by encounters with smaller galaxies. Gaia also measures the temperatures, luminosities, and chemical compositions of vast numbers of stars. Put together, those measurements act like a time-lapse film of stellar evolution and galactic evolution combined. You can see which regions are forming new stars, which are aging and fading, and how chemical elements made in stars have been mixed through the galaxy over time. In a sense, Gaia is giving us not just a snapshot, but a dynamic movie of how the Milky Way has changed and will continue to change. All of this means that Gaia is far more than just a static star catalogue. It is a machine for reconstructing history and predicting the future, from the paths of tiny asteroids to the grand wobble of the entire galaxy. But to truly see into the most hidden parts of the Milky Way, especially the crowded and dusty regions near the centre, we need a different kind of vision entirely, one that can look straight through the dust that blinds ordinary telescopes. Right now, the hidden parts of the Milky Way are the most tantalizing. Gaia can track motions and reveal structures, but it still struggles where dust is thickest. Near the galactic center, clouds of dust turn visible light into a fog. It is like trying to watch a play from behind a curtain. You know something dramatic is happening on the other side, but your eyes just cannot see it. To lift that curtain, astronomers needed a different kind of light and a different kind of telescope. Enter a survey telescope built for one purpose: to see in infrared and map the sky in a way ordinary optical telescopes simply cannot. Infrared light has longer wavelength than visible light, so it slips between dust grains instead of bouncing off them. The result is that regions that look black and opaque in visible images suddenly fill with stars when observed in infrared. What looked like empty voids become crowded city centres. Applied to the Milky Way, this technique turned our dusty, blocked view of the core into something astonishingly transparent. With deep infrared surveys, astronomers have been able to map roughly 80% of the stars in the central regions of the Milky Way, an area that was previously mostly guesswork. Instead of relying on indirect hints, they could actually count and locate millions of stars that had been completely hidden behind dust. The data set that came out of this effort is enormous, hundreds of terabytes of information. Buried inside it are the positions, brightnesses, and colours of stars packed into the densest part of our galaxy. When scientists started to analyse this ocean of data, they saw structures that had never been clearly visible before. New star-forming regions, glowing in infrared, traced out filaments and clusters near the galactic centre. Entire star clusters that were once invisible emerged from the background, some very young and hot, others extremely old and faint. These discoveries forced astronomers to refine their models of how the Milky Way built its central bulge and how gas flows into and out of that region. Infrared surveys also revealed young stars surprisingly close to the central black hole, stars that must have formed in an environment of intense gravity and radiation. At the same time, very ancient globular clusters were identified and characterized more precisely, giving clues about the earliest stages of the galaxy, when it was still assembling from smaller pieces. Some of these clusters orbit on paths that hint at past mergers, linking back to the story of galactic cannibalism. By comparing where stars are, how old they are, and what they are made of, astronomers can reconstruct the sequence of events that shaped the inner Milky Way. Infrared observations showed that the central regions are not just a static, featureless glow. They are structured, layered, and dynamic. Gas streams in along the bar, piles up, forms stars, and sometimes gets blown back out by energetic processes. In other words, infrared vision has turned the once mysterious core of the Milky Way into a place we can actually study in detail. It filled in a huge missing piece of the map that Gaia and other missions began. Yet even with dust pierced and motions mapped, there is another class of objects that transforms our understanding of how galaxies behave on the largest scales, engines so powerful that they can outshine entire galaxies and even appear as tiny star-like points from across the universe. Galaxies are not just graceful swirls of stars and dust. At their hearts, many of them hide engines so powerful that they can outshine every star around them combined. These are quasars, and they are powered by supermassive black holes feeding on matter. When gas and dust spiral toward one of these black holes, they do not fall straight in. They form a rapidly spinning accretion disk where material rubs together, heats up, and releases staggering amounts of energy as light. From far away, that tiny region looks brighter than the entire galaxy that hosts it. A quasar is like a lighthouse on a cosmic shoreline. Even when the host galaxy is faint and barely visible, the central engine blazes across billions of light years. The energy comes from gravity being converted into heat and radiation as matter spirals inward. Magnetic fields thread through the disk and the region above it, twisting and channeling some of that energy into narrow beams. Along the poles of the spinning black hole, these magnetic fields can launch jets of particles moving at speeds close to the speed of light. Those jets shine across the electromagnetic spectrum, including in extremely energetic gamma rays. You might think of these as distant exotic objects that only happen in the early universe. But a more modest version of this phenomenon exists inside our own galaxy. When a stellar mass black hole or a neutron star feeds on material from a nearby companion star, the same physics plays out on a smaller scale. These systems are called microquasars because they mimic the behavior of full-size quasars, just with less mass and on shorter timescales. They still form hot accretion disks, still launch relativistic jets, and still produce high-energy radiation. One of the most famous examples is an object known as SS-433. In this system, a compact object is pulling in matter from a companion star and launching jets of plasma at a significant fraction of the speed of light. Those jets precess, slowly changing direction over time, carving out corkscrew-shaped paths. Observations of SS-433 show emission all the way up to gamma-ray energies, a sign of just how extreme the acceleration processes are. By studying systems like this, astronomers get a much closer look at the physics that also powers distant quasars. All of this energy is ultimately driven by magnetic fields, tapping into the rotational energy of the disk and the black hole. As charged particles spiral along magnetic field lines, they are accelerated to very high speeds and radiate strongly. That process, repeated over and over in the inner regions around black holes, shapes the surrounding environment. Jets can punch out of the galaxy, carrying energy and matter into intergalactic space. They can also heat and stir gas in the host galaxy, sometimes triggering star formation and sometimes shutting it down by blowing gas away. What makes quasars and microquasars so important for our story is not just that they are spectacular. They are key players in how galaxies evolve. A supermassive black hole at the center of a galaxy does not simply sit quietly and swallow matter. When it is actively feeding, it can regulate how much cold gas remains available to form new stars. Too much energy pumped into that gas can stop it from collapsing, slowing, or even quenching star formation. In this way, black holes help decide how quickly galaxies grow and how they age. So when you look at a galaxy, you are seeing a complex feedback loop. Gas falls in, stars form. Some of those stars explode and enrich the gas, and in the core a black hole feeds and sometimes erupts with tremendous power. Microquasars close to home let us test the underlying physics in detail, while distant quasars show us how those processes play out on the largest scales. Together they reveal that black holes are not just endpoints of stellar evolution. They are engines that help shape the fate of galaxies. And that brings us to the bigger question of how galaxies themselves live out their lifetimes, from active star-forming youth to quiet old age. Galaxies are not just static backdrops for stars and black holes. After seeing how collisions, dark matter halos, and central engines work, the next big question is almost biological. How does a galaxy live, grow, and age over billions of years? If you line up different galaxies in the sky, you can almost see stages of a life cycle, from messy, bright youth to calm, faded old age. Spiral galaxies like the Milky Way are in what you might call their active adult phase. Their disks are rich and cold gas, the raw fuel for star formation. In the spiral arms, density waves compress that gas, triggering bursts of new stars. Many of those young stars are hot, blue, and very luminous. So spirals tend to shine with a bluish tint overall. That blue light is a sign that star formation is ongoing right now. Galaxies like this are still very much alive, constantly recycling gas into new generations of stars and back into space through supernova explosions. Sometimes this process kicks into overdrive. In starburst galaxies, conditions line up in a way that causes star formation rates to spike to extremely high levels. Maybe a collision has funneled gas into the central regions, or a tidal interaction has squeezed clouds together. In those environments, gas is consumed at a furious pace, forming stars far faster than in a typical spiral. The catch is that this phase cannot last. It is like burning through a fuel tank at maximum throttle. Within a relatively short cosmic time, the galaxy uses up or blows out much of its cold gas. As galaxies age, many of them begin to change shape. Some spirals lose their well-defined arms and become lenticular galaxies, systems that look like disks without prominent spiral structure. These lenticulars are often a transitional state. They may still contain a disk, but star formation has slowed down. Over even longer timescales and through repeated mergers, galaxies can turn into ellipticals. Elliptical galaxies are dominated by old red stars. Their gas supplies are depleted or heated, so that new star formation is minimal. In that sense, ellipticals are like retired galaxies, no longer building many new stars. A key driver of this evolution is the simple fact that gas is finite. Star formation stops when there is no longer enough cold gas able to collapse under gravity. Collisions between galaxies play a dual role here. They can trigger brief, intense starbursts by compressing gas, but they can also help transform disks into more spheroidal shapes. When two spirals merge, the orbits of their stars can be scrambled, producing an elliptical remnant. At the same time, feedback from supernovae and active black holes can heat or expel gas, making it harder for the merged galaxy to form new stars. As star formation slows, the light from a galaxy changes colour. Young massive stars burn hot and blue but die quickly. Older, lower mass stars are cooler and redder and can live for billions of years. So, as the supply of new massive stars dwindles, the integrated light of the galaxy shifts toward red. That is why many ellipticals appear red and dead. Their stellar populations are dominated by old stars, and their spectra show little evidence of recent star formation. Meanwhile, the supermassive black holes at their centres may continue to grow slowly by accreting leftover gas or stars. Over cosmic time, the general trend seems to be that many galaxies will eventually end up as some form of elliptical or quenched system. Gas gets locked into stars, blown out into intergalactic space, or heated so much that it cannot cool efficiently. Mergers build larger and larger structures while at the same time reducing the supply of cold fuel. If you imagine the very distant future of the universe, most active star-forming galaxies may fade away, leaving behind massive red ellipticals and the relics of their once dynamic youth. So, the Milky Way today is somewhere in the middle of this grand timeline. It is still a spiral, still forming stars, still interacting with smaller companions. Its central black hole is relatively quiet compared to a quasar, but it may flare up in the future. Its gas reservoir is not infinite, and its shape will continue to change as it merges with neighbours. Understanding this life cycle lets us see our own galaxy, not as a fixed picture in a book, but as a character in a much larger cosmic story, one that is still unfolding and will eventually lead into an even more dramatic future. For most of human history, the Milky Way was a blurry band of light across the sky, a mystery we could not step outside to see. Now, after everything you have just explored, it should feel completely different. Our galaxy is not a flat picture. It is a three-dimensional, moving, colliding, growing system that we are embedded inside. It has a history, a structure, and even something like a future trajectory, all written in the motions of its stars and the invisible matter that surrounds them. We began with a simple but profound limitation. Because we live inside the Milky Way, even basic questions like how many stars it contains and how many spiral arms it has turned out to be surprisingly hard. Dust clouds blocked our view, especially toward the center, and visible light telescopes were effectively blind in the most interesting directions. That is why infrared surveys and X-ray observations were so important. They let us see through the dust and into the crowded heart of the galaxy, revealing hidden stars, star-forming regions, and ancient clusters that reshaped our understanding of the core. Gaia took that deeper and turned the problem of perspective into an advantage. By using Earth orbit as a measuring baseline and exploiting parallax, it mapped the positions and motions of over 2 billion stars in 3 dimensions. That gave us not only a map, but also a way to reconstruct the Milky Way's past and project its future. In the tiny wobbles and velocities of those stars, astronomers uncovered the fossil evidence of galactic cannibalism. The strange motions and unusual chemistry of tens of thousands of stars revealed that our galaxy once collided with and consumed others, such as Gaia Enceladus, and is still in the process of absorbing smaller companions. Alongside that story of mergers is the deeper skeleton of dark matter. When we looked at how fast stars orbit, especially in the outer parts of the galaxy, the speeds made no sense if only visible matter were present. The solution was a massive dark matter halo, an invisible structure that envelopes the Milky Way and provides the extra gravity needed to hold it together. That halo helped galaxies form in the first place and continues to shape their evolution, guiding how gas settles, how disks form, and how structures like spiral arms and bars persist over billions of years. At the same time, black holes and their accretion disks act as regulation engines. On the larger scales, quasars powered by supermassive black holes can outshine entire galaxies and drive jets that heat and stir gas. On smaller scales, microquasars inside our own galaxy let us test the same extreme physics up close. These engines are not just spectacular, they influence whether gas remains cool enough to form stars or gets heated and blown out. That feedback is one of the key ingredients that determines how galaxies transition from actively star-forming spirals to quieter lenticulars and ellipticals dominated by old red stars. Putting all of this together, the Milky Way is clearly not static. It grows by consuming other galaxies. Its structure is carved out by gravity, density waves, and dark matter. Its stars move in complex patterns, not simple circles, and their orbits carry the memory of past collisions. Infrared astronomy has revealed a hidden history in the dusty core, and missions like Gaia have transformed galactic science by turning the night sky into a precise dynamic data set instead of a flat backdrop. Future missions will go even further, measuring fainter stars, mapping more distant galaxies, and probing dark matter and black holes with greater precision. So the next time you look up and see that faint river of light stretching across the sky, remember that you are not just looking at a static decoration. You're looking from inside a living system that is constantly changing. Stars are being born and dying, gas is flowing and heating. The central black hole is quietly waiting for its next meal. The galaxy is wobbling, colliding, and slowly evolving. And all of this is happening while we sit on a small planet in one spiral arm, trying to piece together the story from the inside. The universe is far more dynamic, interconnected, and alive than anyone staring at that hazy band of light centuries ago could have imagined.